right, good afternoon, everybody. Thank you very much for coming. Again, my name is Dave Cook. I'm the Director of Undergraduate Research here at UAH. And what we're doing this week is what we're calling virtual outreach program. So this is an opportunity for, again, rising sophomores through newly admitted UAH students to UAH to join some interactive sessions with undergraduates that we have in our Summer Community of Scholars program, and also their faculty mentors as well. So this is a really cool program that we have for undergraduates to do as a UAH student, where you basically in a 10-week program, you work all summer with a faculty or a researcher. We provide a stipend, which is, it's not really salary. It is money, but it's not like you're doing work for pay. That the stipend is to help support you, so to pay rent, so you can buy food, so you can buy gas for your cars, things like that. And the idea is that you don't have to have a job, so you can just concentrate on research the whole summer. So there's some really cool programs. And so today's really cool one, and I can't pronounce the title, and it's definitely not my field, so I'm not even going to try, but I'm going to turn it over to Savannah and Dr. Casper to talk about their project. Please.
Okay. I guess I'll introduce us. My name is Savannah Flaherty. I'm an electrical engineering student at UAH. I'm going into my senior year next fall, and my mentor is Dr. Jason Casabri, and he is a professor at the Department of Mechanical and Aerospace Engineering. And this summer, we've been researching dielectrophoresis. And just in a nutshell, we can make things move without touching them using really strong non-uniform electric fields. So we just wanted to talk with you about that today. So yeah, I don't know how we're gonna like go back and forth with trying to like go over this, but.
Sure. If you guys have any questions, just feel free to interrupt us. But go ahead, Savannah. You're doing great so far.
Okay. Yeah, we didn't get to really talk that much before. Anyway, so we've been researching this because dielectrophoresis is already used in microscopic scales. First of all, the title of our project is Dielectrophoretic control of macroscopic media for in-space applications. And the big deal is that we're trying to use this for larger objects. It's already used in nanotechnology to remotely control very tiny things like cells and like silicon and like nanotechnology engineering. But so far, it hasn't really been researched for use of like large objects, and we think that'd be a good thing to look into. Yeah. So I guess we'll give you a basic overview of what dielectrophoresis is and what it isn't. So
and let me know if I'm advancing the slides right, if you want to go back or forth.
Yeah, it's fine. I feel like I skipped over a bunch of stuff, but I'll just try to go over what it is first. So go back one.
Sure.
So basically, as I said before, dielectrophoresis is a force that all particles experience when they're in a strong non-uniform electric field. I wanted to point out that this is not the same as static electricity, because, you know, you can like rub a balloon on yourself and make it stick to like your sweater, or like when packing peanuts get stuck to you. That's different because that is an applied charge on the object, and the object is like the applied charge on that object is interacting with the electric field. But dielectrophoresis is special because it can work on an object with a zero net charge. And the whole idea is that inside of molecules and particles, even if it has a net zero charge, usually the charge distribution inside of it is different, and it can create something called an electric dipole. And when those interelectric fields are non-uniform, they can move on their own. So yeah, I guess we can go forward. And this is just a picture of what an electric dipole is, since it isn't really useful to try to just talk to you about it. I don't know if you guys have had any physics yet, but actually, have you guys had any physics yet? Like maybe electromagnetism? Okay, well, that's good to know. I wasn't really sure what level y'all had got to yet. So I guess we can go to the next slide.
I was gonna say, I'm not even sure if physics is taught now in high schools. It's
Really?
yeah, it might be something they can elect to take, but I don't know if it's required actually at the high school level now.
I think you're right. I think it's elective. My daughter's taking it this fall, but it's not required.
Yeah, I know that they tried to cram electromagnetism and all of that Newton's law stuff into one semester when I was in high school. I had a really bad time. But anyway, since y'all don't have an EM background, again, here's some more pictures. When we're talking about uniform electric fields, looking on the left side, you can imagine it as being like straight lines that are of even density. But if you look on the right, you can see that they, like towards the center of the point charge, they're more dense. And also for the bottom picture, if you had two electrodes that were close to each other, that have the same charge, they can have uneven electric fields around the fringes. So yeah. And another thing, and it is kind of like hard to like lay all this out because I am not a teacher. So I feel like I am skipping over some things, but I was going to say, sorry, I do
No, that's okay.
presentations.
Well, while you're thinking about what to say next, I'll just say that what inspired all of this work is I saw this video on YouTube of something called the straw trick, where you can demonstrate this. And so it works better in the wintertime, but if you take a plastic straw and rub it on your sweater or your shirt, it picks up a static charge. And if you set it on top of a Coke bottle or something, and you hold it still, and then you bring your hand close, it'll rotate the straw towards your hand. And it only works because of the fact that you've got these fringing fields that Savannah has drawn here. So the field lines have to come out like a bundle of flowers. They can't be straight, otherwise it won't work. They have to sort of come out. So it's the shape of the straw, kind of like this top picture here, that gives you this body force that acts. It's not like magnetism where you have to have a conductor like metal. It works on virtually any material. And so it's kind of an unusual phenomenon, and it basically allows us to create a gravity-like field. It's not gravity, but it's a field like that in which matter will interact and be attracted to it. So go ahead. Would you like me to advance to the next slide?
Yeah, I guess. Yeah. Again, I don't know how deep into it I should get, but yeah, I guess we can move forward.
Oh, you're doing fine.
Yeah. So anyway, this summer, what we're trying to do is we're trying to see if we can predictably and safely demonstrate the dielectrophoretic force on small objects like a marble or a wooden sphere, etc. So in order to do this with these larger objects that have a lot of mass, we need an extremely high voltage generator to generate those powerful electric fields. So actually up until this point, we've been doing a lot of design, just trying to get our test bed set up. So we're gonna see it in like the other slides, but to try to test the force, we made a pendulum, and the pendulum is supposed to, as best we can, represent an object floating in free space. So we had to use a really, really light moment arm and all that, but I'll get to that later. Anyway, so yeah, we had a bunch of problems trying to generate 60,000 volts for our test bed. First of all, I'm not trying to like read off the slides, but most of the things that you can buy at, you know, Lowe's, they're not expecting you to use it for 60,000 volts. I think that we had to get something that was, we're going to see it later, but it's a generator that was like an air purifier. I'm not totally sure how it worked, but we had to use something that was completely not what it was made for. And again, like meters, like you have like your fluke meter or your multimeter, you can't use anything digital because if you put 60,000 volts in it, it's going to die. And electronic sensors, I mean, it'd be really easy to measure the force on something if you could just use a sensor from like DigiKey, but again, sensors are going to get fried. So we had to do it the old fashioned way that we're going to see. We couldn't use any materials that are gonna, we used a pendulum and we're just doing our physics 101 equations to try to figure out the force. You can see the little electrode at the bottom, that's the white thing. And it's coated in PVC clay, which was really kind of shocking to Dr. Castlebury that that would work, because before we had problems with it arcing really badly. Yes. Arts and crafts clay will stop 60,000 volts, but anyway, so yeah, that's the picture of our test setup. And we did have like a lot of problems with arcing, so we had to make sure that metal was out of the way, nothing pointy. Everything is wood. On Friday, we tried to use it and it arced across those 5 resistors actually.
Oh, it did.
Yeah, so we're gonna have to remove the clip. And according to Dr. Castlebury, that was a problem when he was doing it at home because things would catch on fire.
Yeah, I did set fire to my ping pong table on multiple occasions.
Yeah. And also trying to,
Don't try this at home. then.
Yes.
yeah.
Oh, here's a good picture.
Yeah, and those are the little electrodes I made, because that's what I was trying to show you guys before. Those weird electric field lines that were coming, like the ones from the screws, and those are screws underneath, those are going to have a non-uniform electric fields, but those things, those plates right there are going to have something that's more flat and homogeneous, I guess. So like kind of one of our experiments is to try to see if it attracts more to the screw versus the plate. Now, actually, we did an experiment on Friday where we tried to attract the marble to the flat part of the plate, and then we compared it to how it would attract to the edge, and it actually attracted to the edge more. So we haven't gotten a lot of data points yet, but yeah, and that's our generator from China, I think.
Mhm.
And that is our multimeter in the, or off to the left.
You can
And
see
it's
it's an old school analog meter, which, because as Savannah pointed out, the digital ones will get fried because of the high voltage. Go ahead. Somebody was about to speak.
No one? Okay. And yeah, I would like to point out how hard it was to try to even measure the voltage that was going into the electrodes, because Dr. Castlebury did a really good job trying to fix that. Again, multimeters, like the multimeter right there does not remotely go up to 60,000 volts, and you will not find that at Home Depot at all. So we had to get creative with circuits and stuff. Unfortunately, at 60,000 volts, circuits begin to behave in interesting nonlinear ways. So even now, I feel like it's, sorry, go ahead.
No, I was just going to say, I've got a video of us basically controlling and turning off the field so that it lets go. So
Yeah.
I don't have it on my computer, but I can hit play and show it to the camera, and maybe that'll be good enough. So if you just watch the marble, Savannah's going to turn the voltage down and basically turn the gravity off. And it takes just maybe about 10 more seconds. There it goes.
I'm glad you found that. I did not have a good video, so I just left it. Yeah.
Are there any questions?
Why does it have to go all the way to 60 kV?
That's a good question. So it has to do with the force that is predicted to occur. And the force is proportional to two things. Number one is the permittivity of the material. That's just a material property. So plastics have a value that's like 1 or 1.5 to 3 or something. And marble and glass are maybe a little higher than that, but not much. But then the main thing is it varies with the voltage, or actually more properly, the electric field squared, like the gradient of the electric field. And when you punch in all the numbers, you need really high electric fields in order to make it work, which is why I think this is not something that has really come into mainstream as an application, because it's a small force at the typical voltages that we deal with. Like, for example, a lot of what we use as consumers are things like this 9-volt battery. So a lot of your commercial electronics are 3.3. Savannah, correct me if I'm wrong, because you're the electrical engineer. 5 volts, 12, 9. Your wall outlet is 110. Your washing machine is 208 or 220. And so that's just about it. So you only see this voltage, or you only see these forces significantly when you get up into tens of thousands of volts. So that's why I think it's been kind of missed at the macroscopic scale, because not a lot of people know this. But as to why, I guess I could shrug my shoulders and say, I don't know, that's just what the numbers say. So, but yeah, it just requires a very large voltage. And when you punch in the numbers, that's what is predicted.
Thank you.
Yeah, that's a good question.
I have a question.
Yeah.
When I'm just when I printed out the sheet and saw artificial gravity,
Mhm.
I was thinking like use for like human space flight and having
Yeah.
artificial gravity, you know, the sci-fi. But
Yeah.
is it safe to have this much voltage around a person? Just wondering.
That is an excellent question. And in fact, we just submitted this like a 2-step proposal. We step A, and then based on the strength of the proposal and how it's reviewed, step B if we're invited. So this is a proposal to NASA Innovative Advanced Concepts Office, or NIAC as it's called. And it is basically what we're doing is proposing to do to develop an artificial gravity system, or at least explore it for crewed spaceflight to Mars, for example. And the biggest unknown in this is how would a high voltage environment like that affect humans, and could you do it in a way that's safe? And that's a question that we don't have a good answer to yet. So we actually are collaborating with a world-class expert in microgravity effects on humans. And they're really good at understanding the effects of different things on human tissue. And so we're not going to test this on humans, of course, in this first proposal, but we will do a lot of calculations and do a lot of literature review. And we'll probably do some fun things like put a piece of steak on our pendulum and see if we can attract the steak and stuff like that. And I think that the DC voltage that we've been applying probably will not be something you'd want to use, but probably an AC field, one with a frequency to it. There's probably certain frequencies that are healthier than others that will work really well, because we're mostly made of water. So you want to find something that interacts with the blood flow in a good way, so that it kind of promotes good blood flow and doesn't introduce weird gradients or currents in the body. So you ask a really good question that we don't have the answers to, but we actually recognize that's probably the biggest unknown. And so that's something that we're proposing to try to study next. That's an excellent question.
Thank you.
I don't know if y'all can see the chat, but Tyree's asking if it can be less than 60,000.
I think so, depending on how water behaves under various frequencies. The reason that we think that is because the permittivity that I mentioned before, this is a good question, very good question, by the way, is there's a value for the direct, the DC voltage that we've applied and we're studying, but the AC behavior is very different, and it depends on the material. And so we're basically like 70% salt water, essentially. And so how does salt water behave in that environment? What's its effective permittivity as a function of frequency? And can we get away with something that's less scary than 60,000 volts? And I think probably there are some promising combinations of voltage and frequency that would work that don't require crazy high voltages. We just don't know yet what those are, but that's one of the things we want to try to find out. Oh, I moved my screen, sorry. Other questions?
Do you think, sorry, but I just have one more question. Do you think you can use this application to also like make a safer like throw switch in electrical systems, like
I don't know, Savannah, do you have any thoughts about that?
I am honestly unsure. I don't know if I've encountered that yet. What type are you talking about? Because I've heard of that, but I'm not sure how this would apply.
kind of like a circuit breaker in a large system. Like, in Texas, there was that huge outage.
Oh.
So possible uses like that, large scale.
I'm not sure. I've honestly never considered that with this experiment.
There are other applications that could be considered, like treating this as like an electrohydrodynamic pump for pumping fluids. You probably could engineer something to throw a switch mechanically if you wanted to. Another application that's been considered for rocket propulsion is in deep space. When you are in free fall, that's where you experience weightlessness. And if you have a rocket with chemical liquid propulsion in it, it's just sort of floating around in a tank. And if your pump is in a spot where the liquid is not there, it's not going to be able to start itself. And so you have to somehow get that liquid to go back. And so one of the earliest applications considered before this was really like looked at in the 50s and 60s, and then it was kind of dropped and forgotten. But the idea was to solve that problem by putting electrodes on and then having the liquid drawn back down to the pump. So that's an example of where they would look to create a field to actually pull the liquid in towards the pump and solve that problem. So it probably could be used to mechanically throw a switch if you wanted to.
Thank you.
Mm-hmm.
Yeah, and I'll just point out that a lot of times what undergraduates are doing in these programs is what I call applied research. So they're kind of taking a known known things and applying to a specific problem. But it sounds to me like this is something I call like basic research, where they just have this phenomenon. They need to play around just to see how it works and what works better and how it reacts under certain conditions. And then already they have some ideas on how they can apply it, but they're not sure exactly how to do that. So this is a really interesting. Also, students do basic research like this, but I don't think it's as common, and it's really neat to see students get involved in this very, kind of ground floor research in these areas. So, yeah, this is really great. We got another question in the chat. How would the non-uniform field interact with charged or magnetic materials? Oh, Jason's on it already.
I started to, I'll answer it out loud though. I think that it would probably interact in a similar way that other materials do, in that if it has a permittivity in it, it would, permittivity other than one, it would still kind of respond in the same way, at least at first. If as it accelerates with the placement of a magnetic field in there, there could be some other secondary effects of a moving magnetic field with respect to stationary charges on the plate. And that could have some other kind of strange, hard to predict effects that probably for most applications wouldn't be significant, but I don't know. So it's something to look at.
Any other questions?
No questions? All right, well, I just put a link to the Summer Community of Scholars program. So if you'd like to know more about it, if you're going to be a student here in the fall, you can apply for next summer. And another thing is that we hope to have a face-to-face poster session in the fall, but if we're not able to, for any reason, all of the students in this year's program are also creating a video which will go on a YouTube channel. And so I'll be sure to send the link out to everybody who signed to participate in this event. So, but the poster session, if you can come, that's really great, because then you can, meet Savannah and Dr. Casabri and talk to them face to face. It's a lot of fun. So if that happens, I'll be sure to let everybody know when and where that's going to happen as well. But otherwise, Savannah, Dr. Casabri, thank you very much for your time. Everyone, thanks for coming. Yeah, if you're going to be students here, I hope to see you in the fall. Otherwise, have a great week.
Yeah, thank you.
Yeah.
Thanks for coming too.
Nice job, Savannah.
Yes, nice job.
Thanks. I tried.
Take care.
David, I guess I'll see you again in a few minutes. I think the other one I have
Oh, okay.
starts.
All right. Yeah, I'll probably kick you off and I'll bring you back. So
That sounds
All right.
good.
See you
All
then.
right, take care. Bye-bye.